divided by the exact. The trickiest part is that we always mess up or mix around the exact value that we divide by. So I'm going to go ahead and plug that into my calculator. I encourage you to do the same to double check that you get the same answer as me. And I'm going to answer this to 3 significant figures. 0.226% is the answer that we get for our percentage error. I did my subtraction of the numerator first, and then I divided by the exact value, and then I multiplied by 100. It's kind of my thought process, which comes from actually not having this graphing calculator as a high school student, but from the TI-84. It's just easier to do it that way. But yeah, there you go. Now, we've been practicing a bunch with direct variation, and the deal with inverse variation is it's pretty much exactly the same thing. We need to solve for k and put it back into the formula, just that our original formula switches around. But it's still that same process. So we see the weight of an object varies inversely. Okay. Well, varies inversely is y equals k over x, as opposed to k times x. Still that same process of like, okay, I'm going to write out that formula first. And I'm going to deal with that sentence first before I move on. The weight of an object. Y varies directly with x. The weight of an object varies directly with the square of the distance. Square, okay, but x is my distance. We'll have y be weight, w, and x be distance, so we'll have that be d, distance. It could be anything else. If you wanted to keep it as x and y, you could have kept it as x and y. I just think it's helpful when we start dealing with word problems to have variables that look like they should go with what it is. W should go with weight. D should go with distance. I think it helps us keep stuff straight. So I go back in and I say W equals K, and I'll say W as a function of D equals K over, and then we have D in the denominator, but it does say the square of that. So just like direct variation, I'm going to square that distance. First sentence, done. At sea level, which is 6,370 kilometers from the center of the Earth, an astronaut weighs 600 newtons. As always, we'll notice that they start giving us pairs at the beginning, right? And that tells us that we can solve for these. Because it says now find a model for the weight. So we are going to have to solve for k because we want k to be a number. All of these guys are variables. My output, my input, I just want k to be a number. So at the distance, 6,370 kilometers, I have a weight of 600 newtons. So if I plug in this guy for weight, k over 6,370 squared. Go ahead and solve for k. And give me all, don't do it to 3 significant figures. Just tell me the whole thing. So it ends up being a really big number, and spelling it all out or writing it all out, because we know that we want our formula to not have an approximation. We don't want our formula to be a rounded value. We want it to be as exact as possible because we're going to be using this model in parts B and C. So the non-rounded value is 2, 4, 3, 4, 6, 1, 4, and then 4 zeros, which is, well, I don't know, a very large number. Thousands, millions, billions, 24,346,140,000. That's a big number. That's just K. We have not finished our problem because we need to create a model. So we just need to plug it back in to that original guy and just replace K with that number. And now that is our model for calculating the weight depending upon how far you are from the center of the Earth. It says that the International Space Station orbits at an altitude of 408 kilometers. Sorry. Find the weight of the astronaut while on board of the International Space Station. So my thought was 408. That's closer than 6,370 kilometers, right? So that moment of like, that doesn't make sense that somebody in space would be closer to the center of the Earth than somebody from sea level. So it says in orbit, which means that 408 kilometers above sea level. So if we're thinking about sea level on the Earth, right? Here's the center of the Earth. So we know that our radius, in other words, the distance to the core, would be 6,370 kilometers. Then being in orbit, which definitely not drawn to scale, but we get the general idea, will be an additional 408 kilometers, which means that my total distance from the orbit of the space station to the center of the Earth will be those guys added together, which is 6,778. Yeah. Okay. So if we wanted to find the weight, W equals question mark, while they're on board the space station, which means our distance is 6,778 kilometers, we just find W of that, which I think you can do on your own. This just means we're plugging in 6,778 in for D. The weight that we get is 529.94 ish. I'm going to round it to 3 sig figs. So 530 newtons. You could put a little decimal there if you want to show like, hey, that is 3 sig figs, but the grader will know that that's the third significant figure if you're rounding to 3 sig figs. In this class, at least. So you could put the decimal there, or you could just leave it without. All right. Find the required distance from the center of the Earth for the astronaut to weigh half of what she weighs at sea level. So we want to find the distance. We want the weight to be half at sea level. Well, we were given what the weight at sea level was before. It was one of our original values at the very top of the page, 6,300 and, oh no, that's the distance. They weighed 600 newtons. So if we want to be half of 600 newtons, that would be 300 newtons. Okay, so we want to find the distance when we weigh 300 newtons, which means we're plugging in 300 for W. And solving it for this. You should be able to plug this into numerical solve, but it might give you a negative answer. You could always graph this and put this into y equals and this into y equals and find where they intersect, or you could multiply both sides by d squared. And then divide by 300. And then take the square root. And we get approximately, to 3 significant figures, 9,010 kilometers, right? It was 9,008.54, which means that this guy would round up to a 1, and that's 1, 2, 3 significant figures. Okay, sorry for the long video. You guys did a great job today.